So in this video, I'm going to be going over how to use expressions in Ansys and how those can be used to model a glider's performance and calculate various quantities with it, like the glide ratio, and I'll show an equation for how to calculate the velocity, and show how to calculate certain statistics that will be fed into a state space matrix, which I will show later. So first we want to start with a fluid flow CFX and then open the geometry. We should make sure to right-click over the geometry and select New Design Modeler Geometry, since that is the preferred geometry method. Yeah, so now that our geometry file is open, we're going to go to File, Import External Geometry File. And here I've created a plane glider shape called Fuse1. And here you just see a basic plane shape. The main difference being that the wings are flat plates with the back part here angled, and the vertical stabilizer is pointed downwards. I've done this for design reasons, which I won't go into at this moment. Next, we're going to go to Tools and Enclosure, and we're going to generate one real quick to see its basic size. So for this analysis, we're going to want one that is very tall in the Y direction and also gives enough room in the X direction so that the induced angle on the wings is easily visible. So we're going to start by halving the X values in the enclosure size. We're going to slightly reduce the Y values to 0.8. And then we are going to make the Z's much smaller, 2.2 meters each size. And then we're going to regenerate that. And here you can see what that looks like. Next, we're going to create a Boolean. Going to set it to subtract and target the main box and apply. And for tool bodies, the two ways to select it are we can either click over the plane and select below it, or we can choose to select the solid that is the plane and apply the geometry. Then generate the Boolean, and here we have our glider shape. So the next step I'm going to do, which isn't necessarily required, is change my select to faces. Then I'm going to right click and select all faces, and then deselect the faces that represent the fluid box. So this gives me all the faces of the glider. Then I'm going to do a name selection and apply the geometry. Oh, let me redo that. And I'm going to name that plane surface. Generate it. And next I'm going to name all the various inlets, outlets, and fluid walls, which were seen in other Ansys videos, but I'm going to reiterate them. So we select the inlet face, we go to name selection, apply, name inlet, generate. Then we'll go to the back, click, right click, name selection, apply, outlet. Generate, and then select the other four surrounding walls. Going to name that fluid walls and generate. So now we want to save that and name our file glider testing. And now we want to refresh our mesh. We can close our geometry window while we wait for the mesh to refresh. Once we see the lightning icon, we're going to double click on mesh to open the mesh creator. So we're going to close all the windows, given the errors. I'm not sure why it's generating point mass errors on mine recently, but it'll still successfully generate the mesh eventually. So we're going to try generating the mesh as is, and it ran successfully. Here I have it set to display wireframe, and so that's how we can see all these various factors. So we want to save that again, and once it's saved we can exit out of the mesh editor, and then we right click and update. Great, now that we have a check mark, we can edit the setup. And this is the especially interesting step. So first I'm going to define my inlet boundaries. So here is where we're going to change it. We still want subsonic speed, but we're going to change it to Cartesian velocity coordinates. And here I've saved a basic equation that will, we want to select expression, enter that, and we want to, however, this equation goes too fast, it has too high of a frequency. Here you can see a Desmos example. We want our simulation to run slowly so that each step has a chance to update, and we're going to run it somewhere around 100 seconds. So here I've pulled up an equation. So dividing the time by 50, this is all in radians, seems like a good number to approximate it. And then we'll stop our simulation around 80 seconds. I know this equation is hard to see, so I'm going to post what it is in text form over the screen in just a second. We're going to set the horizontal velocity component, which is in -z, so actually we want to change that. Put this, our main velocity component, in here, so it proceeds in -z. Make that negative, and the y component is still normal. Y is positive in the lifting direction, so we're going to maintain that as sine of t over 50 times 1 meter per second, and we will have no x-based velocity. So we can set that to 0. And as we can see, the location and boundary type are both inlet. We'll apply that, make sure to get no error messages, and okay that. If there are any error messages, you should probably try and fix any equations in that step before moving on. Next, we will name the outlet and set the relative pressure to 0. Next, the fluid walls. We'll select wall, then fluid walls, a previous step. You can also use control to select all of the different walls while you're in this step. Then we'll go to boundary details. It's a free slip wall, and okay that. And finally, we'll define a fourth boundary, which is our plane / glider. And it will be a wall located on the faces of our plane, or plane surface. It'll be a no-slip wall with a roughness. So based on research, the sand grain roughness can be approximated like 0.25 millimeters. Make sure to change the units. So we'll apply that and okay it. We also want to make sure to change our analysis type to transient. And our total time I'll set to 79 seconds with a time step of 1 second. And okay that. So here you can see 2 warnings. So we're going to click on those. The first one says, in analysis, flow analysis 1, domain default domain, transient analysis requires that initial conditions are specified unless initial values file is specified at runtime. So we want to go to our domains. Here we can see it here. We'll double click on that. And we can see domain initialization, so we'll set that. So as we had it, it was 0, 0, and our main velocity, which is 7. Actually, I may need to go back and change that, fix that. So we'll apply that. As we can see, the warning is removed. So we can go back to inlets. Yes, so I meant to be 7 as our total velocity. So we'll change these 1s here to 7s. Apply that, and OK it. We can also see output control needs to be edited, so we'll double click on that. And it mentions the transient results file. So we'll create a new one, named just transient results 1, and a time step interval of 1, should be seconds. Apply that, and OK it. And as you can see, there are no warnings and errors. So we're going to save this project. Then we can exit out of it. And go to our solution. This doesn't need to be refreshed beforehand, we can just open it directly. So we're going to start the run and wait. I'm going to speed up the step here. Great. Here we can see that our full analysis has run successfully, and it executed just under 80 steps as we planned. If you've seen my previous Ansys video, you'll see that these variable values do not follow the same path they normally do, where they exponentially decrease. This is because the velocities were constantly changing, so they couldn't settle. However, they generally still remain below 1 times 10 to the negative third, so that's fairly consistent. However, we may want to ignore the final time step, where this was getting around 0 and the velocities were far different. Remember, considering we set it to sine and divided by 50, there are going to be extreme vertical velocities at some locations at certain times. So we can exit out of this step and go to our results. So first I'm going to select plane glider. Here you can see our plane defined, and this is where we're going to define our contours as well. We want to generate a solution report and then go to contours. We'll name the first one pressure contour. Variable is pressure. We'll generate 300 contours and put the location on the plane glider. And here's our pressure distribution. So now that we've seen that, we're also going to generate another one called turbulence contour. Check turbulence eddy frequency. Set it the location to the plane. And here we can see a lot generated on our vertical stabilizer. For simplicity, I didn't curve this, it's just a flat plate, so that's to be expected. So a lot near the tail, not so much on the wings and fuselage. And turbulence kinetic energy, however, is not giving as is not displaying results as well. Going to increase the contours and save the eddy frequency. We can also generate vectors. around the plane, apply that. Yes, make sure to set the location to the default domain. Yeah, so here we're mostly getting dots. This is because the velocity changes a lot through the time, so it makes it a lot harder to see. We're also going to generate streamlines, starting from the inlet, and we'll generate 250 points, and forwards and backwards direction. As you can see, we're getting very interesting velocity, interesting streamlines. So next we want to go to the case comparisons. This allows us to view it at different times, and we can click on various times and see different results. Here, at around 31 seconds, you can start to see spiral formations starting near the bottom. This is because there's no way for the pressure to escape on the outside, even though there is a vertical velocity heading towards it. And as you can see, as time progresses, this effect magnifies and it starts a spiraling vortex. So on future analyses, we're going to want to change this from a free slip wall to something that can have pressure escape. So we can also go to our report viewer. And here it generates the total forces, so 3.4 times 10 to the 8th, negative 9.6 times 10 to the 7th. We can also generate an animation of our plane and how the time steps change it. So first, however, we're going to increase the number of streamlines to 250, and apply that. So here you can see a lot more, and now we'll play the animation. So now I'm going to show how to create an expression. So we go up here to the top. And here I've previously created one that will generate in forces. So we want the force in Y on our boundary, which is the plane and glider. So we'll apply that. Yes, so yep, so after some slight editing, here we have the Y force on our plane. And we're going to rename the expression lift. And next we're going to create a similar one to that. So we'll click on expression again, and we're going to name this one drag. And so it will be in the Z direction. And we're going to add a negative sign because the force of drag is in the negative Z direction. And we're going to apply that. And now we have our two equations. So we're going to save our results. And we're just going to show the inlets, outlets, and boundaries again real quick for a refresher. Let me know in the comments if any of these are hard to see. I'll probably paste pictures of a more close-up version of these later. I should mention that the surface roughness will change depending on which material the glider is made out of. So now we're going to save this simulation setup. And once that's done, we can exit out. We then want to clear any results and reset the solution. And then we can double click on it to create a new solution. And we'll start the run again. Yes, so here you can see I've formatted text that will read out the expression values for lift and drag, and then place them on this screen here. And hence I will run an animation that will then show the changing lift and drag values. So they can be recorded in an Excel document, which will in turn give the lift and drag values. which can be used to calculate various quantities.